So we're going to be talking about collisions. Let's look at one. Example 1 says, in the collision seen below, which vehicle experiences the larger force? The truck, the car, or both the same? Hopefully we'll all get this one right. What's the correct answer, folks? Oh, do we need to vote? Who says A? Who says B? Who says C? Okay, all of you voted C. Why? Okay, if you said forces come in pairs, I would give you full marks. If you nerded out and you said, hey, Newton's third, and dropped the mic and walked off, because Newton's third says that forces come in pairs, I would give you full marks. This is often referred to as, for every action there is an equal and opposite reaction, which I just find so confusingly worded. And why are you using the word action and reaction in the same sentence? Because I might get those confused. Ugh. Okay. Here's the question that we want to answer then. Yesterday, I think I talked about a bug hitting a bus and going splat. Why is it, if the force is the same, why is it that the car and the car driver are almost always worse off after the collision? That's the question. Is the force the same? Everybody say yes. Yes? What's different between the truck and the car in terms of physicsy things, variables? Oh. F equals what? So if they both have the same force, but if this truck has a bigger mass, what variable has to get smaller in the force equation?
Time.
Time's not in the force equation. F equals what?
MA.
So if m gets bigger, what variable gets smaller? F equals what?
MA.
So if for the truck, so let's write this. The force of the truck equals the force of the car. For the truck, really big mass, tiny acceleration. For the car, tiny mass, really big acceleration. And so when it comes right down to it, when we're talking about collisions, what does the damage? The impulse? No. The force? No. The acceleration? Yeah. And that's why the bug goes splat, because it has so little mass that it has to go through a huge acceleration. In fact, it accelerates so much that its exoskeleton can't handle that, and its exoskeleton crumbles, splat. Where the bus, you know what, does it accelerate backwards when it hits the bug? Technically, but if you try to calculate it, it's so small, people on the bus don't feel the impact of the bug shuddering through the frame. Okay? I think I promised you yesterday that I'll explain in the next lesson why the bug got damaged. It's the acceleration. Alrighty. We're going to introduce the notion of what we call a closed system. A closed system or situation is one that's cut off from the outside world. It has no external forces. There is no F applied coming from off the page. Examples: frictionless surfaces like ice, outer space, because that's really frictionless. Systems floating on the water as long as they're barely into the water. So if it's floating right on top of the water, like styrofoam, and there's very little of it under the water, that will be nearly frictionless, and that will be almost a closed system. And rolling objects. If we have a closed system where there's no external forces, there's no F applied coming from off the page, we can say the following. The contact forces are governed by Newton's third. So forces are equal and opposite. That also means that impulse, momentum change, is also equal and opposite. Because if the forces are the same, and if it's the same collision, I think it's reasonable to assume that the time of the collision is the same for both of them. We end up with the impulse of the first one equaling the impulse of the second one, but one's positive, one's negative. If the truck loses 100 kilogram meters per second of impulse, the car gained 100 kilogram meters per second of impulse. we have a fancy word for that. When momentum doesn't vanish, when it only gets transferred from one to another. What does it mean to say that momentum change is equal and opposite? If the car loses 20 units of momentum, what happens to the truck? And Austin, I deliberately didn't say gains 20 kilogram meters per second. This works for any units of momentum in whatever system you're in, imperial system, metric system. If you're making up your own units, this is a universal law. What that means is, since momentum change is equal but opposite, the momentum for a closed system is neither gained nor lost. It's just transferred from one object to the other. And this is what you can write in the bottom. In other words, momentum is conserved. This is the law of conservation of momentum. It's a universal law. It's hugely handy. It's hugely useful. Among other things, this will be our tool for analyzing collisions between two objects. This is part of what police would be, or RCMP would be using in crime scene accident investigation. Car accident investigations, definitely. Momentum is conserved. Turn the page. Wait a minute, Mr. Dueck. What, Alex? In this picture here, the final velocity of the truck is 0. So, Alex, if the final velocity of the truck was 0, what's its final momentum? Also. And the final velocity of the car is 0, what's its final momentum? So what's my final total momentum if I go 0 plus 0? So what must my initial momentum have been? 0. How can that be? We have vehicles that are moving, Mr. Dueck. See the argument? The law of conservation of momentum says this. If momentum final is 0, the momentum initial had to be 0. How can that make sense? Momentum is what times what? It's okay. It's on your sheet, which is why I told you to get your blue sheet out. By the way, next time look at your sheet before saying, I don't know. Hint, hint. Okay, so here's what we have. We have the momentum of the truck initial and the momentum of the car initial. That's before the collision. You okay with that? Yeah? Bam! They collide. After the collision, they come to a stop. So the final momentum is 0. What that means, Nick, is the initial momentum must have been 0. Alex, momentum is what times what? What's the mass of the truck initially? What's the velocity of the truck initially? Plus, what's the mass of the car initially? What's the velocity of the car initially? It's not 24. What, Thomas? I've told you direction and vectors make a big difference now. It's negative 24. And I don't think you even need a calculator for this. I think what you get is 24,000 plus negative 24,000. What's 24,000 plus negative 24,000? Is it possible to have a total momentum of 0 with more than one moving object? Oh, heck yeah, but you better believe one of them must have been moving in the opposite direction. And so momentum was conserved. We didn't gain momentum. We didn't lose momentum. We finished with 0. We started with 0. So the law of conservation of momentum says this. In any collision or explosion in a closed system, no external forces, momentum is conserved. That word conserved in science is a very specific meaning. It means you neither lose nor gain. You may have in chemistry learned about the law of conservation of mass. When you're doing an experiment, you neither lose nor gain mass because atoms can't magically vanish. They can bond with other atoms. They may go from solid to gas or from liquid to solid, but the mass can't change. Well, in physics, there are conservation laws as well, and one of them is conservation of momentum. It says the total momentum you start with has to equal the total momentum you end with. And so you can write this in several ways. You can write in English, the total initial momentum of a system has to equal the total final momentum of a system. Do any of you think that I'm going to write that out in English ever? No, I tend to abbreviate. You can write it mathematically as saying momentum of object 1 initial plus momentum of object 2 initial equals the momentum of object 1 final plus the momentum of object 2 final. That's pretty good. The fourth way, since momentum is mass times velocity, you can write it as m1v1 plus m2v2 initial equals m1v1 plus m2v2 final. I'm going to pick the shortest one, the third one. It also introduces a new symbol to you. Those of you that have done some Math 12 may have seen it before. I don't think you've seen it in Math 11, but you may have. Does anybody know what we call that symbol? It's a Greek letter, sigma. By the way, when you type it, it looks like that, but we're lazy in math. When we handwrite it, it often just ends up being a capital M on its side. We don't put the little droopy down and the little lifty up on either end because we're in a rush. And you can sort of see, this is where our capital letter S came from, sigma. If you just kind of stop writing that, you can see it turns into an S over time. So this is called a sigma, but it means something in math and physics and science. When you see this, what does it mean? Yeah. Or, if you want to write it even shorter, total. You read this as your total initial momentum equals your total final momentum. So I'm going to use this one. This is the one that I put on your formula sheet. I think if you look right next to the impulse equation, I wrote it this way, yes? And that shouldn't be a surprise, Austin. I tend to abbreviate, and also high nerd content. I'm teaching you Greek letters, so of course I'm going to do that. If you want to, I have no problem if next to that on your green formula sheet you write out this one or you write out this one. I'll live with that because I know this is a situation where my nerdishness might overcome clarity. You might find it easier to think of it as M1 V1 initial plus M2 V2 initial because M1 V1 final plus M2 V2 final. But really, we're going to adapt it for whatever we need. When do we use this? We use the law of conservation of momentum when there is a collision or an explosion. In short, we use it when there is a jen. So if I see a collision or an explosion, that's not the job for a free body diagram. I'm not going to start to defic. I'm going to say this is a job for conservation of momentum. There is a lovely example of the law of conservation of momentum. It's a toy called Newton's Cradle. This is used in collisions. We're going to start today with pictures, and then next class we'll do word problems. And actually the word problems I find easier than the pictures because I'm good at spotting the units and directions and just picking the stuff out. But here, it says, find the missing velocity, magnitude, and direction. We have a before, a collision, and an after. What are they asking me to find? I think the velocity of object A after, because that's where the question mark is. You see it? All right. Now, we're going to do this the long, meticulous way. Eventually, you'll start to take shortcuts, and in your homework page, if you want to take shortcuts, go ahead. In our notes, we're going to be very meticulous. And so the first thing, Rohan, I would ask myself is this a collision? Rohan, you're going to say yes. Say yes. Rohan, Before the collision, that's this picture, what's moving? Car A, car B, both or neither? Actually, sorry, even before we do that, is this a collision? Say yes. This is a job for conservation of momentum. I'm going to write down the total momentum we start with has to equal the total momentum we finish with. And you can see my sigma symbols look like that. Technically, it should look like that, but no one writes it that meticulously anymore. You can if you want to. Draw an arrow. We're going to break this up further. Now, Rohan, we're going to say, before the collision, what's moving? Car A, car B, both or neither? Look, both. Before the collision, are they stuck together or are they separate? Now, when will you see them stuck together? Later on, you're going to see a picture like this. Here, they got stuck together after the collision. So we always ask ourselves, what was moving before and stuck together or separate? So you told me that both were moving and separate. So I'm going to say there was momentum from object A initial and plus there was momentum from object B initial. Is that all right? Good. Wham! They collide. After the collision, what's moving? Car A, car B, both. Really, Mr. Dueck? Every collision? Probably. Car A, car B, both or neither. Looking at the picture, I think both and I think separate. So, momentum of car A final plus momentum of car B final. You may reach the point after you've done a few of these where you can skip writing this line and go straight to that line. Okay. Alex, momentum is what times what? So momentum A initial is going to be mass A V A initial plus momentum of B initial is going to be mass car B V car B initial. Wham, they collide. Momentum of car A final, Rohan, is going to be mass car A V car A final plus mass car B V car B final. Rohan, what am I trying to find? Which one? There's 4 of them. Can you please be more specific? Let's all put a little dot above that guy. That's what we're going to get by itself. I think the whole left side is going to drop down like a domino first. Yes? And then, how will I move this MA over right there? How will I move this plus MB VB over? Which one am I going to do first? Reverse bed mass. We'll divide last. You can almost see the equation. So, Rohan, the MA VA initial drops down plus the MB VB initial drops down. Now, what am I going to write? What did you say I'm going to do now? Minus MB VB final. By the way, you'll notice this equation does not show up on your formula sheet. Why would I make you memorize a specific situation when you can derive it from scratch? And then what? Mass A. And then, Rohan, do you mind? I'm going to put the velocity of A final on the left-hand side right there by itself, because that's usually where we're used to seeing the thing that we're trying to find. Folks, you've come a long way. Had I done this with you in September, that would have seemed so terrifying or intimidating. You can't see Rohan's face, but he's almost looking at me bored. Like, really, Dueck? Yes, I can rewrite this. So, well done. Now it's plug and chug. Rohan, what's the mass? You know what? I don't think I'm going to fit it in. I'm going to need to move down a line. So VA final. What's the mass of car A from the picture, Rohan? What's the velocity of car A? plus, what's the mass of car B? What's the velocity of car B? Please be careful. Is it 2? Which one? Positive 2 or negative 2? Why must it be negative? Because you let the 10 be, and that arrow is pointing to the right, and the 2 is pointing to the left. Yes? So, folks, we got to start being paranoid about direction. Negative 2, which makes a huge difference to what this is going to work out to. And then there's a minus sign and another 2,000. And then can you look at the velocity of car B final? Get the sign correct. What's the velocity of car B final? That's negative? What did you call that direction? So which one, negative or positive? As soon as you committed to that being positive, you committed. Now, Mr. Dueck, here's what I would have, now that you know to look for signs, Rohan, here's what I would have done. Look up, look up, look up, look up. As soon as I saw this picture, I would have gone, okay, positive, negative. I'm going to get a negative answer. Oh, wait a minute. No, I'm not sure because this arrow goes both ways, but that's positive. And then I'm going to remind myself if I get a negative answer, that'll be backwards. If I get a positive answer, that'll be forwards. Okay? Okay. So, positive 4, yes? Okay. And then divided by 1,000. I really encourage all of you to get your calculators out and try this. Although I think I can do this in my head. It's going to be 10,000 minus 4,000, which is 6,000. Minus 8,000, which is negative 2,000. See, I'm getting negative 2 in my head. Double check me. I see one person nodding. I see 2 people nodding. These diagrams will work out nice. I don't care enough about you to make your word problems next class work out evenly. So if you get decimal answers, that's just Mr. Dueck not caring. So don't be scared. But here, negative 2 meters per second. If you had to assign a direction to that, what direction is negative 2, Rohan? What direction is negative? I don't know. What did you decide? Don't ask me. Look at how you assigned the values. Look at the 10. Which way is the 10 pointing? You made that positive. So which way did you make positive? So which way is this negative then? To the? Yes. So you could say 2 meters per second left. I would give you full marks. I would probably say backwards just because the picture makes it look like the car went backwards. In fact, here's what happened, I think, in that collision. Car A is going forwards. Car B is backing up. They hit each other and they bounced apart this way because car B ended up going forwards and car A ended up going backwards. So here's the collision. Bang! Yeah, that I can wrap my brain around that. That makes sense based on car crashes I've seen in the movies. Yeah. And then I'll put a box around my final answer. There's my touchdown dance. Let's do another one. So the law of conservation of momentum. When do I use it, Austin? If I see 2 objects in the question and they collide. If I only see one object, it's probably impulse and momentum, but not the law of conservation of momentum. Cool. Cool. Nick, let's do B together. Looking at picture B. Is there a collision? 2 objects is a job for conservation of momentum. I'm going to write the total momentum that we started with has to equal the total momentum that we finish with. Nick, before the collision, what's moving? Car A, car A, car B, both or neither? Stuck together or separate before the collision? Must be because they're heading in opposite directions. Okay. So I'm going to have car A initials momentum, momentum of object A initial, momentum of object B initial. Bam! They collide. After the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? This is still showing, oh, definitely separate because they're going in opposite directions there. Okay, so I'm going to get car A's momentum final and momentum of car B final. Alex, momentum is what times what? You may find as you do a few of these that you can visualize both this step and this step in your head, and you can go straight to saying, hey, it's the mass of car A, velocity of car A when we start, plus mass of car B, velocity of car B when we start, initial, equals mass of car A, velocity of car A final. That's a terrible messy, Mr. Dueck. And mass of car B, velocity of car B final. Nick, what are they asking me to find here? That guy. What's going to drop down like a domino? The whole right side, then? What? Yeah. Is that okay? You've come a long way. So I'm hearing Nick say, Mr. Dueck, look, the mass of object, the whole right side just drops down. Then we would subtract the mass of car B, velocity of car B initial, and then we would divide by the mass of car A. Oh, and then let's write down VA initial. And again, Rohan, notice I keep putting these vectors on the velocity to remind myself I better pay attention to direction. Talk to me, Nick. What am I going to write? Mass of car A? Okay. Final velocity of car A? Negative, so you're going to let to the left be negative. That's fine. We'll be consistent for the rest of the question that way. You could have let left be positive and right be negative. I don't know if I would have done that because that might be confusing to me, but okay. So -2 plus mass of car B, final velocity of car B, pointing to the right, minus 2,000. What was the initial velocity of car B? -3. It was going backwards or to the left? Yeah. All divided by 1,000. How fast was car A going and what direction? What was its velocity? I think I can do this in my head. It's going to be -2,000 plus 8,000, which is 6,000, plus 6,000. You get 12? Or am I wrong? I don't see anybody nodding, maybe. I see one nod for 12, 2 nods for 12, 3, okay. Positive or negative? I should have asked that. I got positive, yes? Okay. So in this situation here, oh, direction forwards. Or you know what? No, we used left and right last time, didn't we? Is that what we used? Let's go to the right. In this situation here, if I look at the diagram, then car A was coming in really fast. Car B is still backing up. Wham, they collide. Car A went off here. Car B went off here. Car A almost stopped and only bounced back a little bit, but car A had enough velocity that it transferred a lot of the momentum to car B. Example C. Example C. Iman, is this a collision? Is there more than one object? This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Chris over here just yawned. Let's see if we can take a shortcut because Chris is getting bored. Instead of writing the P's, let's see if we can go straight to mass times velocity. So you ready? Before the collision, what's moving, Iman? Car A, car B, both or neither? Stuck together or separate? So I'm going to write mass of car A, velocity of car A initial, and I have mass of car B, velocity of car B initial. I took a gamble. I skipped writing the letter P's out. Bam! They collide. After the collision, what's moving? Car A, car B, both or neither? Both, stuck together or separate. How would I show stuck together? Look up. Mass A plus mass B, V final. They must be going at the same velocity if they're stuck together. Oh, stuck together, what's that mean mathematically? In brackets. Come on, what am I trying to find? Talk to me. How will I get that by itself? Well, what's going to drop down like a domino? The whole... Okay, so you know what? I might even do that, just absent-mindedly go, well, it's going to be plus, bracket, MA plus MB, close bracket, V final, took care of that. Now what? Now what? Good. And that's going to be the initial velocity of car A. I have a feeling it's going to be big-ish because car A had to bring car B to a stop, send car B going forwards at 5 meters per second, and have enough momentum itself left over for itself to also keep going at 5 meters per second. My guess is there's probably going to be an initial fairly big velocity. Let's find out. Velocity of car A initial is going to be 2,000 plus 4,000. V final 5 minus 4,000. Aman, what's V initial for car B? Thank you. You caught the negative. All over the mass of car A, which is 2,000. I think I can do this one in my head. It's going to be 6,000 times 5. It's going to be 30,000 plus 12,000. 40, 21? Yeah. Direction to the right or forwards. Or east. I tend to go with right and left because I rarely mix those up. I have mixed up east and west all the time because my brain is dumb. Unless the question uses the words east and west, then I'm stuck with it. D. Last one. When I was 6 or 7, I used to do this. We called it ghost riding. You would get riding on your bike really, really fast, and then you would try and jump off and see if the bike would keep going. Any of you do that when you were 6 or 7? A couple of you, okay? We were smart enough to do it on a grassy field, so at least we wouldn't scrape the bike up on the pavement, or if we took a tumble, we'd rather take a tumble on the grass. And we would, who can get their bike to go the furthest without anybody pedaling, right? Dumb games you play when you're 6 or 7. So, we're pedaling. Ah! After. Is this a collision? Actually, what this technically is an explosion. An object came apart. This is a jeune. This is a job for conservation of momentum. I'm going to remind myself that the total momentum before equals the total momentum after. Caleb, before the collision, I guess the letters we're going to use are R for rider and B for bike. So before the collision, what's moving? Mass R, mass B, both or neither? Stuck together or separate? So my initial equation is going to be the mass of the rider and the mass of the bike, the initial. Ah! After the explosion, Caleb, what's moving? Mass R, mass B, both or neither? Stuck together or separate? I'm going to have mass of the rider, velocity of the rider, initial, plus mass of the bike, velocity of the bike. Initial. Final. I'm also going to make a bit of a prediction. Look at the rider. Did the rider gain momentum or lose momentum? Did the rider in the after speed up or slow down? So did the bike gain momentum or lose momentum? The bike must have gained. Yes? Alex, momentum is what times what? I don't think the bike gained mass. You know what? I can tell you this answer is going to be bigger than 5. The bike is going to speed up. And I noticed that as a kid, that if I jumped off, as long as I didn't drag my feet accidentally while doing it, if I managed to jump off perfectly and land on the ground without touching the ground after I got off the bike did speed up as it went away from me. Yes, it has to. Okay. What are we trying to find? Caleb? Talk to me. Or as we like to call it, the whole left side, and then we don't have to read out the whole thing. Yep. What, that drops down like a domino. Then? Then? And then that equals VBF, but I'm going to try and wedge it in over on the left because that's where we're used to seeing the thing by itself. So our prediction is it should be bigger than 5. Let's plug in the numbers here. VBF equals, what was the mass of the rider, Caleb? Plus bike? Heavy bike, but that's okay. V initial? And you've just decided that to the right is positive. Minus 60 mass, velocity of the rider? Still going forwards? Divided by 20. Yeah, I can do this in my head. It's going to be 80 times 5. It's going to be 400 minus 120. It's going to be 300 minus 20. It's going to be 280 divided by 20. Yeah. 14, I think. Anybody else with a 14? 14 meters per second to the right. So the fact that momentum is conserved, that I know that the total momentum I start with has to equal the total momentum I finish with, Robert, that means that if I know 3 of the velocities, I can always find the 4th. Hugely useful. What's your homework? I think every question here. Yeah, every question. There is, I did pretty good actually, 15 minutes left. You can get a big chunk of this. And the take-home quiz, if you haven't done it already. Our goal is, so I see you next week, Tuesday and Thursday. I'll try and set this up so that Thursday you're not going into the long weekend with a whole bunch of homework if I can avoid that, okay? Conservation.